Hello, I'm Michael O'Connell, and in this video I want to continue examining substitution and elimination reactions in greater depth so that we can really nail down this concept and understand it. So let's take a look at this reaction. We have our starting material. The first thing we want to do is make sure that we have a good leaving group, which we do. We have chlorine that is certainly going to leave. Now, the next thing we need to do is identify the carbon bearing that leaving group as primary, secondary, or tertiary. And we see that this carbon atom obviously is bonded to our leaving group, but it has two methyl groups here and here. And then it's also bonded to a carbon that is part of our cyclohexane ring, which means that it's bonded to three carbons, which means that it is tertiary. So that eliminates one of our reactions, which would be the SN2 reaction, which will not occur with a tertiary alpha carbon. The next thing we have to do is look at our reagents. So we have the number 1 here, which means that this is the first reaction that we're going to perform, and that's with NaH. So we know that these are going to break up into their ions, so we'll have Na+, which is going to be a spectator ion, and then we have the rare, not so often seen, H- anion. What is that going to do? Well, I can tell you that this lone pair of electrons is not going to behave like a nucleophile, actually. But I can also say with certainty that because H2 is a very stable diatomic molecule that we're all familiar with, that is what our H- anion is going to want to become to be as stable as possible. So what that means for us is that this H- anion is going to want to pull off a proton and behave like a very strong base. And because it's charged, we can definitely believe that it's going to behave like a strong base, so that also eliminates the possibility of an SN1 or an E1 reaction. So because of that, we're left with only one possibility, which is an E2 reaction. And that is exactly what is going to occur. Now, we have to think about what proton is going to be removed. And remember, we have to remove a proton from a carbon atom that is adjacent to the alpha carbon atom. Because the two methyl groups are equivalent for our starting material, there's really only two protons we can consider removing here. So we have a proton on our methyl group that we could remove, or we have this proton that we could remove. And what we need to figure out is which proton, if removed in the E2 reaction, would create an alkene that will be more stable. What this would mean is that the double bond will have more substituent groups. So if we removed this proton, right, these electrons would go in here. Our leaving group would be leaving simultaneously as this all occurs, so we don't have to worry about that. So you would have your cyclohexane ring, and then that, and then your methyl group, and then your double bond, right? So as you can see, this is just 1 and 2. You only have 2 substituents. That's not bad. Over here, you just have the 2 hydrogens. Okay? So that gives us 2 substituents for our double bond. But what if we removed this proton? So if we removed this proton, the electrons would go here, right? So let's see how many substituents that would give us. So we have our cyclohexane, we have our double bond here, and then we have the methyl group there, and then again, we didn't do anything to this methyl group, so it'd still be there. Whoa, that's a lot more substituents. That's way better. Because look, here's the sp2 hybridized carbon in the alkene, right? The double bond. And then it has a carbon here, carbon here, carbon here, carbon here. Tons of substituents. It's perfect. It's exactly what we want. Okay, so that's going to be a way more stable alkene. So that's the product that would form from an E2 reaction. So let's draw that mechanism, right? And I'll keep that arrow there forming that double bond because that's certainly what's going to happen here. So this lone pair here, negative charge, lone pair is snatching this hydrogen this double bond is forming, and then this group is leaving all at the same time. It's one step, there's one transition state for that E2 reaction. Okay, perfect. And as we just drew on the board, we know what our product is going to be. So I'm going to draw that one more time for us because I added a little spice to this problem, a little blast from the past, where we're going to do an alkene reaction, just to keep us on our toes because we're going to have a final exam coming up fairly soon. Okay, so perfect. There we have it. We have an alkene, and now we have our second reaction that's going to occur. So we have Br2, and we have water in excess. Okay, so hopefully you remember when you have a Br2, or we represent halogens as X2, you're going to form a bridge, right? So again, if we were being really specific, what happens? Because of the polarizability of the electron clouds, you get a partial positive and a partial negative, okay? So that's what's really going on there, by the way. And what will happen is this alkene, or the double bond, the lone pair, the pi electrons in here will grab one of the bromine atoms, and then this pair of electrons will go to that bromine, which can handle and delocalize that negative charge by itself there pretty well. Okay? And what happens though is this other pair of electrons will bond as well, such that we get a bridge, right? I know that the arrows really are not great. That's why you draw the bridge. It basically happens all at once. You just draw it in one step. So we don't want to worry too much about that. But what we would have is, again, we have our cyclohexane, and we have this, and then we'll just draw it down, right? Okay, and obviously this has two lone pairs of electrons, and you can calculate the formal charge. It's going to have a positive charge, and you do need to show that if you're drawing a reaction mechanism. You certainly will get points off. In our reaction, we have water in excess, so that is what's going to attack here, not one of the bromine anions that would be left in our reaction mixture. So we have our water, and we know that the oxygen has two lone pairs. And we also know, if we remember this from alkene reactions, that one of these lone pairs is going to attack the carbon atom with more substituents. Now, I'll be honest with you, I actually don't know which one it would favor here, because this has two substituents, in a sense, right? Because this carbon has a carbon bonded there and a carbon bonded there. And similarly, this carbon has two methyls. So I'm going to be honest with you, I'm not really sure exactly which one it would attack. That might be something I might learn in organic chemistry too, or I may be just incorrect. And if that's the case, I'm very sorry. But either way, the concept that I've relayed to you is correct, that it's going to attack the more substituted carbon atom in this alkene reaction. Now, for our purposes here, since I don't know, let's just indicate what would happen if it attacked this carbon, and then we'll do the other carbon as well, just for practice. So if it attacked this carbon, then this pair of electrons would go back on the bromine, and then we would get a product. So that product would look something like this. Okay, so we would have a alcohol group there. Yes, I'm ignoring proton loss for now. And then we have that coming off, and then this is going to have the two methyls, and then the bromine. Okay, so that could be a product, right? And then if it attacked here on this carbon, then this would go on our bromine, right? So we could get this product, in which we have kind of the same thing, really. It's really just that alcohol group and the bromine trading places. So you have those two products possibly. I might be correct that those are the two products that would form here. But the important thing is just remembering that concept of that lone pair of electrons attacking the more substituted carbon atom that's in the part of the bridge, right? And the other important thing to always remember is look to see what's in excess, right? because I know if that weren't there, right, if we didn't have water, it would just Br2. Of course, that bromine anion that's left in our reaction mixture would attack the more substituted carbon atom that would be part of that bridge that formed as well. But hopefully, again, that this whole reaction that we just did is a good example for you to look at when you're thinking about not just the substitution and elimination reactions, but also alkene reactions as you're studying for your final exam. Here is another reaction worth considering. As you can see, we have our starting material, and obviously it's an alcohol. But when you look at this, hopefully there's something that screams out at you. What you hopefully recognize is that OH is a terrible leaving group. So we have to look at our reagents to see what is going to happen here. So we are reacting this starting material with sodium hydride first. So let's see what we can do with that. As I said in the previous example, the hydrogen has a lone pair of electrons and a negative charge, and it acts like a base. So it's going to pull off a proton from our starting material. Now we have to look at our starting material and figure out which proton is it going to remove, aka which proton is the most acidic. And that's going to depend on what atom on our starting material can bear a negative charge and remain the most stable. And obviously, all we have that can do that is the carbon or the oxygen. Obviously, there's 3 carbons, though, so we would have to choose between those. But fortunately, we don't have to do that because we know that oxygen is more electronegative than carbon. So the proton attached to our oxygen is going to remain the most stable with a negative charge. So that's the proton that our H- is going to remove. So we can draw that, right? Okay, and then the bond between these will go on our oxygen, right? So really, we're going to get this molecule, okay, where we have 3 lone pairs on our oxygen. Then we're going to react this with CH3CH2Br, okay? And hopefully, you're seeing this come alive. Things aren't as bad as they seem, are they? Right? Take a look at this. Don't get too confused. Well, this, we could say, is something we should recognize as we have an alkyl group and then an oxygen with a negative charge. Okay, negative charge, so this is certainly going to be a strong nucleophile. But also what we have is we have CH3CH2Br. We know that Br, oh, it's a great leaving group. So we know that this would be represented by this, right? If we were to do our line angle formula for this compound. And what we can see here is that this is our alpha carbon, the carbon bearing our leaving group bromine, and it's primary. And we know that we don't have some giant sterically hindered, very, very large base. So we know that it's not going to be an E2 reaction, obviously because our alpha carbon is primary, it can't be E1 or SN1, so it's just SN2, okay? And fortunately, the RO-, in this case, this compound, is a very strong nucleophile, so it's perfect. So what is going to happen? Well, if we were drawing out this mechanism, right, we have this compound here. What's going to happen is as your bromine leaves simultaneously, one of these lone pairs on the oxygen is going to add to that carbon that was bearing our leaving group, okay? And then that is going to leave you with your major product, which in this case is going to be an ether, okay? And actually, because we have 1, 2, 3, 1, 2, and 3. Notice I'm just being very, very careful to make sure I don't miss a carbon atom, right? Because here we know that we have 2 carbon atoms, 1 and 2 on this side, and then we add our nucleophile, the oxygen, or the lone pair of electrons on the oxygen, but we have 1, 2, and 3. 1, 2, and 3 carbon atoms to account for. But this is going to be your final product. This is the last reaction that I want to do in today's video because it involves a reagent that I think is worth talking about for a moment, and that is toluene sulfonic acid. And sulfonic acid derivatives are extremely acidic, okay? And specifically, this is one that you'll commonly see abbreviated as TSOH, okay? And as you know, this is toluene, right? It just has the methyl, okay? And then the sulfonic acid part is going to have something like this. Okay. So your acidic proton, right, is here. Okay. And hopefully that just gives you some context to this reaction that we're about to perform. Now, we do need to remember, as I just said, that these sulfonic acid derivatives are very, very, very acidic. And that's going to be very helpful for us because let's take a look at this reaction. Because, not going to lie, when I first saw this, I was a little scared. And hopefully you may have been too, for the right reason. Because when we look at this starting material, there's no leaving group. So I was like, what the heck? What am I going to do? But fortunately, we have toluene sulfonic acid, right? Because what we see is all that this whole molecule has is it has this double bond. So it has pi electrons. And when I see a double bond, I know that the pi electrons can act as a nucleophile and it can grab something. So what is it going to grab? Well, it's probably not going to grab methanol because methanol, like water, it's not very acidic, it's not very basic, so it's probably not going to pull off a proton from the methanol. But I know it'll certainly pull off a proton from the toluene sulfonic acid because I just said that it's very, very acidic. So we can start there and just see where that takes us, right? Okay. So once we grab that proton, we would get something like this, right? Hopefully I keep remembering that that oxygen is there. Now, here's the big question, right? Where are we going to put this positive charge, right? Which carbon is taking this hydrogen? Well, I'm going to put the positive charge here, okay? And you might ask, well, why am I going to do that? Well, the reason I'm going to do that is because this is going to be more stable than this if we had the positive charge on the other atom. Okay? And let me show you why that is. This is a real blast from the past, as I always say, because this is going to be a resonance structure, right? We have a lone pair of electrons here that can form another double bond, and then the positive charge could be on our oxygen atom, where we would get this. Okay? Now, the reason this is more stable is due to the resonance structure that is able to be formed here. We would have some sort of resonance hybrid by which this positive charge is delocalized over two atoms, which just stabilizes it. Unlike this, where this positive charge here, it's localized. This is sp3 hybridized, this is sp3, 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 sp3. Everything else is sp3 hybridized. So that positive charge is just stuck on that carbon atom, which means it's electron deficient, it's just less stable. So this is the cation that we are going to form. Now, that's all well and good, right? And we know that this is probably going to be the major contributor out of these two resonance structures. Why? Well, oxygen's more electronegative than carbon, so it's not really going to want to have a positive charge on it necessarily, even though the resonance hybrid does have that positive charge delocalized. But anyway, we would have this cation, right? Now that we have our carbocation, we need to figure out what is going to happen next. Now, the toluene sulfonic acid had its proton removed, and that is favorable because we know that the equilibrium always favors the reaction of a strong acid to form a weak base. So that is why whenever you saw reactions, maybe in general chemistry or even in organic chemistry, in which you have like some sort of acid on one side and then another acid on the other, and they give you like this pKa is 50 and this is 15. The equilibrium favors the side with the acid or conjugate acid that has the higher pKa value, which means that it's the weaker acid, because the equilibrium favors the reaction of the stronger acid, okay? So that's important to remember, because what that means for us is that this TSO minus anion that's floating around, that is not really going to do much, is it? It's not going to attack this positive charge because it's pretty stable as it is. It's already favored by the equilibrium, as I just displayed. So we need to think about our methanol, and that's why I put it in square brackets up here, because I want to remind my little brain that this is what we need to focus on. Now, methanol, we know, is a weak nucleophile and a weak base. So we know that it's a weak base. So with our molecule here, and especially since there's no other groups coming off of this ring, it's certainly not going to pull off some sort of proton. That is definitely not going to happen. It is such a weak base, okay? But we do know that although it is a weak nucleophile, this oxygen has 2 lone pairs, okay? And that is going to be enough in this case. This lone pair on the oxygen atom is going to attack that positive charge. And then we would obviously have some sort of proton loss. And you would get your major product, which would look like this. Okay? So you would have the OCH3, and then you would have your oxygen in here. So if you were describing this type of problem on a test, you would need to specify that the reason that this molecule wouldn't be your product, where you would have had the positive charge up there, right? So the reason that this is not a product that will be formed, this isomer, is because this carbocation is stabilized by resonance, and the other carbocation that I had before is not stabilized by resonance. So because of that, this is the product that we get from this reaction. So hopefully these last 2 reactions that we did in this video really help you become a little more comfortable when you're given some sort of starting material and it looks kind of scary because it doesn't have a leaving group. Usually you just need to calm down, think about what material you have, especially always look at your reagents. Often they are going to be a huge, huge source of information for you in figuring out what's going to happen. And if you would like, you can check out a video I have that is specifically for that purpose, where I describe the trends for nucleophilicity, basicity, and leaving group reactivity. Because once you understand those, you will become much more comfortable with substitution and elimination reactions, especially because on tests and exams, most of the time, they're going to give you carbocations, or I shouldn't say carbocations, but alpha carbon atoms that are secondary, because any of those 4 possibilities are reasonable depending on what reagent you have, because they're really trying to test that you understand what a good nucleophile is and what a strong base is, what a weak nucleophile is, that sort of thing. So I really, really hope that all of this was helpful for you. I know this video is kind of long, but I think these 3 reactions will hopefully help you get a better understanding of what you can do when you're given a starting material that doesn't have a leaving group that is very apparent. So thank you so much for watching.